He's going to talk about the comprehensive detection and mapping of the quantitative trait loci, improving the photosynthetic ability in high-yielding rice. So please welcome Dr. Toshio Yamamoto.
Thank you very much, Dr. Yano, for a kind introduction. And I'd like to thank Dr. Pichard for giving me an opportunity to talk here. Now, I'd like to introduce our current status of trials to understand the genetic basis of photosynthetic capacity in high-yielding rice. Okay. Photosynthesis is one of the toughest traits for genetic dissection. This slide is a simple summary of complexity of photosynthesis. Net assimilation rate here, NAR, is a major determinant of crop growth rate, CGR, which leads to the final yield. And NAR could be categorized into leaf photosynthesis rate and canopy structure. And leaf photosynthesis rate is further divided into CO2 exchange capacity, senescence, and midday depression. And these characteristics influence each other by diffusive conductance caused by stomatal size or density, or the amount of Rubisco caused by nitrogen uptaking, and so on and so on. So we don't know what and how in these factors actually contribute to final CGR by through of NAR. Photosynthesis is also influenced by genetic background or the environmental condition. Therefore, the evaluation system for photosynthesis has long time been sophisticated. Gas exchange analyzer such as Leica 6400, like this photo, is one of representative of the authorized equipment. However, this kind of machine needs several times to stabilize the environmental condition in the chamber before starting actual measurement, which makes it difficult to apply the large number of samples directly. These two concerns, complex and delicate, have made photosynthesis trait difficult to treat genetic dissection. In order to carry out genetic dissection of photosynthesis successfully, we consider the following two aspects. From the point of experimental materials, we should use the existing high-yielding cultivar with high level of photosynthesis as a parent, and reciprocal experimental population with uniform genetic background is preferable. From the point of trait evaluation, since genetic analysis requires large number of plant samples, so we sometimes must develop an evaluation system customized for high throughput measurement. Then integrate and compare the detected QTL information on the same genetic map. Okay. First, I'd like to explain the plant materials examined. We choose two cultivars for the analysis: Koshihikari, top variety in Japan, and Takanari, a high-yielding variety also cultivated in Japan. Takanari attains about 30% higher yield than Koshihikari in average by good performances of both leaf photosynthesis rate and light intercepting characteristics. This figure shows the CO2 exchange rate during the stage of booting to maturity in Takanari, black bars, and Nippon Valley, the white bars. The Takanari keeps high level of leaf photosynthesis all the time. Additionally, these photos show that Takanari has an electrotype of leaf body and a large panicule compared to Koshihikari. Both varieties are well adapted in Japan, and the Japanese scientists have accumulated a lot of knowledge about yield components under various culture conditions. By using these two lines, we prepared reciprocal backcross inbred lines, DILs. The F1 plant of koshihikari and takanari it was crossed with koshihikari or takanari. Then the progeny was forwarded by SSD to BC1F6 and surveyed their genotypes by 140 DNA markers. The orange in this figure shows the region of koshihikari, and the blue indicates the region of takanari, respectively. This series of 287 lines were mainly used for the QTL analysis. We also developed reciprocal chromosomal segment substitution lines, CSSLs. The reciprocal BC1F1s were further backcrossed to BC4, followed by additional 3 or 4 self-pollination with careful marker-assisted selection. This series of 41 and 39 lines includes a part of donor chromosomal segment and a uniform genetic background. Once a certain phenotypic difference is appeared in a certain line among this series, the gene involving the phenomena could be located on the substituted region. Okay, now I explained programs, strategy, and the materials. After this preparation, we started actual analysis for the traits listed here: canopy temperature, stomata density, and leaf inclination angle. Parallelly, we explored QTL for leaf photosynthesis rate and characterized the most prominent one. Additionally, we tried to combine the two photosynthesis QTL by gene pyramiding. Okay, first story is about canopy temperature. The infrared thermometer has historically been used to monitor the response of drought stress in many crops. But the leaf temperature reflects the heat of evaporation taken by transpiration, which could become an index of degree of stomatal conductance. Therefore, it also could become an indirect index of varietal difference of leaf photosynthesis in rice, even under well-watered conditions. In fact, a certain level of correlation between stomatal conductance and canopy temperature difference is recognized among rice varieties, and koshihikari and takanari locate both sides of the graph. Infrared thermometer enables to monitor multiple rice plants at one time, which is good advantage for QTL mapping. So we cultivated DIL population with check variety and carried out QTL analysis for canopy temperature. Okay. On sunny days before flowering stage, we took the thermal image photos just above the field from the gondola of crane car, like this photo. And as compared with koshihikari, the check variety, some of the lines showing lower temperature, like takanari, were to be an important factor for increasing the diffusive conductance. This photo shows a microscope image of leaf surface of koshihikari and takanari. And I emphasize the position of stomata by the colored circle. You can see the number of stomata between small vascular veins in takanari is larger than that in koshihikari. Okay, we thought that the number of stomata may be influenced by the leaf size, especially in leaf widths. So we also checked leaf widths. QTL analysis in the BIL population revealed that the QTL changing number of stomata but not changing leaf width were constantly detected on chromosome 6 and 7. Interestingly, the QTL on chromosome 6 increased the number at takanari allele, but another QTL on chromosome 7 increased it at koshihikari allele. Currently, since our interest is effective QTL and the koshihikari genetic background, so we focus on the QTL on chromosome 6. Same as the case in the canopy temperature, we selected two CSS cells, replacing the long arm of chromosome 6 by Takanari genome. On the left side graph of this slide, you can see these two lines significantly increase total number of stomata as well as the average number of stomata. Moreover, one of the line, SKT24, indicates the relatively higher level of photosynthesis than koshihikari, even though it doesn't catch the level of Takanari. Of course, there are still a lot of genes on the substituted region. So we cannot conclude this improvement was really caused by the changes of number of stomata. We continue genetic dissection of this trait by developing further recombination lines, as I show you in the previous case of canopy temperature. Okay, next trait is a leaf inclination angle. Leaf inclination angle, one of the major factors for light interception characteristics. And since leaf inclination angle has shown to be related with canopy extinction coefficient, we try to find QTL for leaf inclination angle. But it is laborious work to measure the degree of the degree of laminar joint in the field with keeping the reliability. So we must consider how we measure it quickly with confidence. And we developed a special application for a smartphone. Now iPod or iPod Touch has a function of 3-dimensional gravity sensor. When we put it along with the leaf blade and touch the panel, it measures and records the degree automatically. Now we could evaluate it during the growth stage, or the leaf blade and leaf sheath main column and tiers without stress. The 2 years test by using the reciprocal CSS cells showed similar result, and the most stable data was the flag leaf at 3 weeks after flowering. Koshihikari shows about 50 to 60 degrees, and on the other hand, Takanari shows about 80. The difference between them are only 20 to 30 degrees, but we found several significant regions. And the direction of all the detected QTL were increasing the degree by Takanari allele. And these three regions, which is a large effect QTL, were detected in both the reciprocal CSS cells. We thought that this trait has a relatively simple genetic basis. Okay, now we have demonstrated several examples of QTL involving leaf photosynthesis, but the most important one is leaf photosynthesis rate itself. So we tried to evaluate it by CO2 gas exchange analyzer. This slide is a summary of our 4 years trials. The 2 years QTL analysis by using reciprocal BILs were conducted on both 2009 and 2010. Additional 2 years evaluation by using reciprocal CSSLs were also conducted by both 2011 and 2012. If you look at this map carefully, you find some trends about the genetic basis of leaf photosynthesis rate. I mean, we see stable QTL among the reciprocal background are on chromosomes 4 and 7. And we also find stable, but only one side background are on chromosomes 1, 2, 3, 10, and 11. Additionally, as for the parent, Takanari is extremely higher photosynthesis, but as for the QTL, there are some QTLs which are positive at koshihikari allele. From the next slide, we conducted further analysis focusing on the QTL on chromosome 4 here. That is the most stable and prominent one. We tentatively named this QTL GPS and characterized it again by reciprocal CSS cells. When the GPS is substituted from koshihikari to Takanari, leaf photosynthesis increased about 20%. On the contrary, when the GPS substituted from Takanari to Koshihikari, it decreased about 20%. The flowering time between these two lines are not so apart, which implies that this change is not derived from a pleiotropy of flowering time or the related environmental conditions. By careful observation of leaf morphology, when the GPS allele is substituted from Koshihikari to Takanari, leaf blade changes dark, narrow, and thick. On the contrary, substituted from Takanari to Koshihikari, leaf blade changes pale, wide, and thin. Simultaneously, we found Takanari allele increased the number of mesophyll cells by the cross-section image, and as well as showed larger slope on the CA curve. This implies that GPS is thought to increase photosynthesis by increasing leaf mesophyll cell number. We are under progress to identify this gene by map-based strategy. Okay, next we examined whether the effect of QTL for leaf photosynthesis rate could be accumulated. Habataki is a sister variety of Takanari, and it also shows high level of leaf photosynthesis. And we detected 2 QTL controlling leaf photosynthesis on chromosomes 4 and 8. And each QTL has a positive effect for improving leaf photosynthesis compared to Koshihikari. And we combine these two lines to produce the pyramiding line here. And the effect of this line increased additively and attained the level of Habataki. This successful result is one of the case study, so we cannot conclude this. We cannot conclude the genetic basis of leaf photosynthesis in rice yet. However, we have some positive feeling for improving source capacity by DNA marker-assisted selection. Okay, our final interest is to confirm whether some of these QTL really contribute the actual yield. We have just started mass scale yield trial by using reciprocal CSS cells. This figure is a tentative summary of grain yield production last year. And we would say that there are no one and only QTL that can explain final yield production. However, even though the effect is too small, once we found the correspondence of final yield and the components, like what I explained today, we can forward next phase to do detailed analysis to make clear its relationship. We are now just after second harvesting of these CSS cells in Japan. Okay, I'd like to close my presentation with summary. The measure QTL for canopy temperature and stomatal density may contribute to leaf photosynthesis. And leaf inclination angle may be a simple genetic basis. And a measure QTL for leaf photosynthesis on chromosome 4 involves leaf morphology. And pyramiding line combining 2 QTLs for leaf photosynthesis showed more photosynthesis rate. Based on these progresses, we are now going on the gene isolation and evaluate their phenotypic performances by using NILs and combine them with some of the QTL, especially in the sync-size QTL. Okay, I'd like to introduce the collaborator. Dr. Kondo and Ika contributed developing the experimental materials and QTL analysis, canopy temperature, stomatal density. Dr. Tanabata contributed to the software development. And Drs. Adachi and Okawa, QTL analysis of leaf photosynthesis and leaf inclination angle. And QTL pyramiding of leaf photosynthesis with Professor Hirasawa. And Dr. Takai and Kondo contributed to development of experimental materials, mapping and characterization of GPS and QTL analysis of grain yield production. And Dr. Yano supported us with variable comments. Thank you very much for your kind attention.
Thank you very much, Dr. Yamamoto, for the excellent presentation. So we have a lot of time for the discussion. Any comments and questions? Yeah.
I have actually several questions. Question number one, how did you measure the photosynthetic rate in a population study? In a big population, you have many plants, many lines. How did you take the measurement?
Measurement of what? How
did you measure the photosynthetic rate?
Photosynthesis rate.
For many plants in the population.
Yes. We used the Leica machine, the 6400. We do all the photosynthesis rate by manual evaluation by using the Leica machine.
So one at a time, or how many machines you have?
How many? One plant, one samples?
No, how many machines? You have to measure them simultaneously.
Okay. So, yeah, the population size of back cross inlet line is 87.
87?
Yes.
You have 87 machines? No.
Yes. However, the flowering tank, the heading date is a little bit segregated. So the range of heading date is distributed among 1 week or 10 days. So some of the line, for example, 20 or 30, one day we evaluated one day, and next day we evaluated another 30 or 40 or something like this we did.
So another question, how are your substrate correlated with yield or plant performance or plant biomass, whatever performance you are measuring?
Excuse me.
Okay.
No.
So how are the substrate, like the one you measure canopy, temperature, stomata density, and photosynthetic rate, are they correlated with yield or biomass?
Biomass. Yeah. As I show you the final slide of my presentation, we are now under evaluation of the relationship between the trait that we have measured and the final yield or yield component. We don't have any data to say the evidence or the relationship.
Okay, thank you.
Any other question? No question? So if no, so thank you again for Dr. Yamamoto for the presentation.